Hi everyone, Nathan here with ATC Cooling and Heating in Kingsport, Tennessee. Today we're going to look at how to design a residential duct system for an addition or a section of the house or even the whole house. One of the problems with duct design is that everyone uses a different measuring stick. Some contractors talk CFM, others talk BTUs and static pressure. Still others will represent duct measurements with feet per minute, or FPM they call that. With the right math, all of these measurements come together and they make sense. But I'll give you what I think is the easiest way to know how to do duct design. But first, let's start with some definitions. CFM stands for cubic feet per minute. It's a measurement of air volume. FPM stands for feet per minute. That's a measure of airflow speed or velocity. BTU stands for British Thermal Unit. It's a measurement of heat content. And lastly, we'll also talk about static pressure, which is really just a measurement of friction loss in the ducts. BTUs, or heat content, is perhaps the most direct approach, but it gets really confusing between heating season and cooling season. When considering air conditioning, it's easy because most air conditioning equipment is designed with about a 20-degree delta T. That's the difference between the input temperature and the output temperature. If it comes into the system at 80 degrees and comes out at 60 degrees, that gives you a 20-degree delta T, for example. In heating systems, different units heat the air to different temperatures, thus you get very different amounts of heat energy in the same volume or velocity of air. A heat pump may only heat the air to 95 degrees or about a 30-degree delta T, while a gas furnace gets to maybe 110 degrees, that's maybe 45 degrees for a delta T. An oil furnace, though, well, that really cooks the air up to about 140 degrees, 75 degree delta T. Very, very warm. When designing a system, it's important to know both the requirements of the AC system and the heating system, preferably in CFM. And of course, different climates demand more than one of the other, more heat or more cooling, depending on where you're living. So instead, let's talk velocity, or FPM, as the one that's easy to understand and converts quickly to CFM, or volume. You can measure FPM, feet per minute, with a simple handheld anemometer, and you can get those for only about 30 bucks on Amazon. Here's an example of one right here. That's the $30 one that I would use from Amazon. Now, once you know the velocity of a duct, or how fast the air is moving through it, you only need to know the size of the duct, and then you can have the CFM, or the volume of air that it's moving. And it's really CFM that equipment, furnaces, air conditioners, heat pumps, whatever, that those equipment units are sized to. So, let's do an example. Say I'm at a register, an outlet register, and then that register is fed by a 6-inch metal pipe. I use my anemometer, and it gives an average reading of 600 FPM. Next, I look at my ductulator, which is available in a handy chart. Here's an example right here. This one is made by Air Distribution Institute. Here's another one right here. This is more of a sliding scale unit. And this one is made by ATCO. You can use one of these charts, or you can just go online to ductulator.com. I'll put a link in the description below for you, and you can look things up from there. So, take your chart or look online at ductulator.com and look at 600 feet per minute, and then cross-reference that with 6-inch metal pipe. And you will see that you're about 100 to 110 CFM. That's an important number, remember that one. For reference, we are looking at branch lines, and they are expected to have an average velocity of about 600 or maybe as much as 800 feet per minute. And main trunk lines, well, they have a slightly higher velocity. You can expect those to be 700 to 1,000 feet per minute. Side note, this is for residential equipment, residential applications where the sound that they make is really rather important to keep down. Industrial, commercial equipment can have a higher velocity and they make a little bit more noise, and it's not a big deal in those applications. So, as for friction, so the other number that we have talked about, there are lots of opinions on the best target to use, but most industry professionals prefer something in the 0.05 to 0.1 inches of water per 100 feet of duct. For most applications, I use 0.08, and using 0.08 gives you the same CFM output as a 6-inch duct at 600 feet per minute, or that 100 CFM or so. So extrapolating these numbers, if you were sizing a duct system for a 2-ton heat pump, you would be looking at enough branch lines to distribute 800 CFM. You can do the math easily. It's really just 400 CFM per ton. 3-ton unit, for example, then would be 1200 CFM. But back to our 2-ton unit, at about 100 CFM per 6-inch line, you would then need 8 branches and outlets to get to 800 CFM for that entire system. A caution here on flex duct. Lots of systems get installed with flex duct, and flex duct has a higher friction loss and thus doesn't carry as much air as a metal pipe. A 6-inch flex line installed properly, which is to say it's fully stretched out, is more like 85 CFM per run. And if the line wiggles all through the attic and thus it's not stretched out, it can diminish to just 50 CFM or even less. Thus, you may want to add a 9th line to your hypothetical 2-ton system or upsize a few of the lines to 7 inches to get to the same output of air. The math for main trunks, that's very similar. A trunk capable of delivering 800 CFM, you just go back to your ductulator and look for a velocity of around 700, 800, 900 feet per minute, and you will see that the recommendation is for a 14-inch round pipe or an 8x20 rectangular duct. Usually ducts are in 8 inches or 10 inches depth. If using flex, well, then a 16-inch round pipe would be better than that 14-inch metal pipe. Okay, let's look at some rules of thumb that we have in duct design process, and then we'll do the example that I've got drawn on the board here. Number 1, avoid too many elbows and hard turns. As you can imagine, elbows and hard turns add up to greater friction loss and thus reduced airflow. Avoid a T if possible. You don't want your air to go smashing into a T. You want it to use a sweep so that it moves out of the system more easily. Avoid going too long. Any line that's 100 feet from the source, from the heat pump, the furnace, that's probably too far and it'll have a hard time delivering airflow way out at the end of that line. Next, downsize your trunk to maintain airflow as you go along. No trunk line should be the same size for more than 25 feet without a reduction. So we'll show that in the example too. Next, don't install branch lines at the very end of a trunk. So for example, if your trunk goes to the end like this, maybe it's an 8x16 trunk, you'll want to bring your branch lines off the end here and leave at least 18 inches before the end. Do not install your 6-inch trunk line or branch line off the end of the trunk. This messes up the velocity inside the trunk and you'll get wonky duct delivery throughout the system. Don't do that. Okay, let's look at our example on the board. Let's say that you have a house that calls for 34,000 BTUs of cooling capacity and 45,000 BTUs of heating capacity. Now you know this because you ran a manual J load calculation on your home, and that took into account all sorts of things, like, for example, the sizes and the direction of windows in the house, the square foot of the overall structure, the insulation factors in the wall and the attic and the floor, the duct location, is it in an attic, is it in a crawl space or a conditioned basement, and of course the climate that your house is installed at. This means you'll be using, in this application, a 4-ton heat pump system. So we've got a 4-ton system here, and that's sized a little bit bigger than the cooling load because, well, we need it for heat at 45,000 BTUs. A 4-ton unit at 400 CFM per ton tells us that we need 1,600 CFM overall delivery. Now, if you ran that load calculation room by room by room, you would know in every individual room how much CFM you need. We're not going to go quite to that depth here, but we'll show you how this works out as we put together our duct system. So the air handler is located right here, not quite in the middle of the basement, but that's where it's located. We've got one branch line that comes out this way and another one that goes further down. From this one, we're going to install 3 6-inch runs. Earlier we talked about the runs, and we're going to say that a 6-inch run can deliver for us about 100 CFM. A 7-inch run, for example, gets you to 150. An 8-inch run gets you to 220 CFM. Again, at our about 600 feet per minute velocity. So I've got 3 runs here. You can pull out your ductulator, go to that website, and you can do the math, because with 3 runs I need now 300 CFM to come through this one trunk line. And that would tell us that this trunk line needs to be 8 by 10. So we've just sized this end of the unit. Now we've got the other end. Now 300, so if I started at 1600 CFM and I just did 300, the rest of this system needs to deliver 1300 CFM. The easiest way to do it is to go backwards, right? So let's say on this run we end up with 3 6-inch runs. Again, 300 CFM, and we've already done the math and we know that that is an 8 by 10 trunk at that end of the unit. Now, we've upsized and upsized this thing twice in order to account for the distance of this run. So now we need to look at the middle section here. And at the middle section, I've got a 7-inch run here, a 7-inch run here, and let's say another 6-inch run here, right? 150, 150, and 100 gets us 400 CFM, right? 400 CFM plus the 300 CFM that we've got on this end. This trunk line's got to carry all of that, so I need to size that for about 700 CFM. Looking at your chart, we get to about an 8 by 20 trunk line for this section right here. Now, if you add all that up again and you see what's left over here, let's say we end up with 2 6s. For fun, let's put an 8 in here. What is this? 100, 100, 220, and we had 700 out of our 1300 that we had to do, so we've got 600 to go to, that's 4, maybe another 8-inch, right? If you go back to your ductulator and look it up, and you add all of these things together, 4, 5, 600 CFM, plus this, you need a whole total of 1300. You're going to make this trunk 8 by 30. Now, it would be easy enough to say we're going to use 10-inch duct, or we're going to use round duct. You can mix and match as is needed, but the idea is to develop a system that flows across the house with equal pressure in each section of the duct, and each of these runs is sized appropriately for the room and for the house overall. You know now that you've designed a system that develops 1600 CFM. It's perfect for your 4-ton heat pump system, and it's perfect for your house. Now, obviously, we're just scratching the surface of duct design, but this is the math, and it works all of the time, not depending on what sort of house you might have. Now, if you need help with a duct design project, or really with anything HVAC, leave us a note here, or visit us on our website, which is atcservice.com. Thanks for watching.